SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss about heat transfer from non-zero pressure gradient surfaces. Now, by non-zero pressure gradient surface, what we mean is the surface on which fluid is flowing, on which heat transfer is also taking place. The surface has a curvature, and due to that curvature, for example, here we can consider convex surface very close to a surface which is similar to cylinder, outer surface of a cylinder, and here we can see that up to some point we have negative pressure gradient or favorable pressure gradient, and beyond that point, because the effective area is increasing, we have basically positive pressure gradient surface or adverse pressure gradient surface. And when we have negative pressure gradient, that means favorable pressure gradient, basically the term del 2 u del y2 at the wall is also negative. But when we have positive pressure gradient surface or adverse pressure gradient surface, this term del 2u del y2 at the wall is positive. Now, for the case of a boundary layer on a flat plate, all of us know pressure gradient of the external stream is 0. Now, in the curved surface that we have already shown, upstream of the highest point, the streamlines of the outer flow converge, resulting in an increase of free stream velocity and a consequent fall of pressure with x. Downstream of that highest point, the streamlines diverge, resulting in a decrease in basically uppercase U and a rise in pressure. In this section, we shall investigate further the effect of the pressure gradient on the shape of the boundary layer profile or the velocity profile within the boundary layer. And we know the boundary layer equation is given by u del x plus v del u del y equal to minus 1 by rho del p del x plus nu del 2u del y2, where the pressure gradient is found from the external velocity fluid as dp dx equal to minus rho u, uppercase U we are using because it is no longer u infinity, it is free stream velocity, but it has a local variation with x, so rho u del x, with x taken along the surface of the body At the wall, the boundary layer equation then becomes mu into del 2u del y2 equal to del p del x. So again the same picture. So since del p del x is favorable, pressure is decreasing, and dp dx is negative, say up to this point. So on the surface all over, the flow will accelerate because of favorable pressure gradient, and also we will find from this equation, since del p del x is negative, del 2u del y2 is curvature is also negative. Now, as the velocity profile has to merge smoothly with the external profile, the slope del u del x slightly below the edge of the boundary layer decreases with y from a positive value to 0. Therefore, del 2u del y2 slightly below the boundary layer edge is negative. Equation which we showed then shows del 2u del y2 has the same sign at both the wall and the boundary layer edge, and presumably throughout the boundary layer. That means this is the scenario. So you can see variation of u, variation, this is under favorable pressure gradient, that means del p del x is negative, and del 2u del y2, that is basically having negative value, and slowly you can see it becomes 0. Now we go back and see what happens in contrast. In contrast, for a decelerating external stream where the flow doesn't accelerate, decelerating external stream, the curvature of the velocity profile at the wall is del 2u del y2 positive. Decelerating, this is with adverse pressure gradient where dp dx is positive. Since dp dx is positive, del 2u del y2 at the wall is also positive. Now curvature changes sign somewhere within the boundary layer. In other words, the boundary layer profile in a decelerating flow, positive pressure gradient, adverse pressure gradient flow, has a point of inflection where del 2u del y2 equal to 0. Now this is a scenario. Here we can see velocity profile is like this because it is under adverse pressure gradient, dp dx is positive. So pressure is increasing, flow in the x direction, and flow is decelerating. This is typically the profile of del u del y, but the curvature is positive at the wall, but finally at the free stream it has to be 0. This positive to 0 transition takes place once it becomes negative, and then again it slowly reduces and becomes 0. So this is called point of inflection. And for the adverse pressure gradient, whenever we get point of inflection, we also get flow separation, or this is onset of separation at the wall. The slope of the velocity profile in the figure suggests that an adverse pressure gradient tends to increase the thickness of the boundary layer, and this increase in thickness of the boundary layer can be further understood with the help of continuity equation. So from continuity equation we can get V velocity is given by minus del u del x integration from 0 to y dy. Compared to a flat plate, a decelerating external stream causes a larger minus del u del x within the boundary layer because of the deceleration of the outer flow adds to the viscous deceleration within the boundary layer. From the above equation, we observe that the V field directed away from the surface is larger for a decelerating flow. The boundary layer therefore thickness not only by viscous diffusion but also by advection away from the surface, resulting in a rapid increase in the boundary layer thickness with x. If P falls along the direction of the flow, that means dP dx is negative, and we say that the pressure gradient is favorable. If, on the other hand, pressure rises along the direction of the flow, we say that pressure gradient is adverse or uphill. We have been discussing this. The rapid growth of the boundary layer thickness in a decelerating stream and the associated large V field causes the important phenomena of separation, in which external stream ceases to flow nearly parallel to the boundary surface. Get this understanding that for the adverse pressure gradient, flow will decelerate, and this adverse pressure gradient may be such that deceleration finally results into boundary layer separation. Over a circular cylinder, we see all these effects. Now, let us start with a consideration of creeping flow. That means Reynolds number is very small, 1 or less than 1, around a cylinder, characterized by Reynolds number less than 1. Reynolds number, we can say free stream velocity, that means the approach flow velocity into the diameter of the cylinder by nu. This is based on the upstream velocity and the cylinder diameter. Vorticity is generated close to the surface because of the no-slip boundary condition. It's obvious. In the Stokes approximation, this vorticity is simply diffused, not advected, which results in a fore and aft symmetry. Fore and aft symmetry. So for a very low Reynolds number, flow smoothly divides and reunites, creating a symmetry between fore and aft of the cylinder. But if we increase Reynolds number, we start observing formation of vortices behind the cylinder. This is just onset of formation of vortices, and we can say at a Reynolds number, as the Reynolds number increased beyond 1, the vorticity is increasingly confined behind the cylinder because of advection. For Reynolds number greater than 4, two small attached or standing eddies appear behind the cylinder. The wake is completely laminar and the vortices act like rollers over which main stream flows. We can see formation of this. This is of course reasonably large Reynolds number. The formation of vortices take place around 4. This is beyond 4, and we can see around 10. As such, this is a sort of mystery or challenging determination through experiment or through numerical simulation to find out the onset and then the Reynolds number at which the vortices just initiate or vortices are formed. Here we can see 10, and literature says it is greater than 4. Depending on the accuracy of the experiment, accuracy of computational tool, it is very close to 5 or 6. Exact values are not concluded. As such, I can show you some of our computations here at IIT Kanpur, which was published in Journal of Fluid Mechanics. We found out this initiation of vortices or the discernible vortices when they appear. We tried to identify that, and we found, definitely we confirmed with the literature, our value confirmed with the literature value, it is greater than 4, but we found exactly at 6.5. You can see 6.3, 6.4, 6.5. This is magnified picture behind a cylinder. As such, if you go back by this scale, it is much smaller than these two vortices. It is at 10, and what we showed, basically we found at 6.5 just initiation of two symmetric vortices behind the cylinder. You can see how much magnification was done because the back surface of the cylinder is looking almost like a straight surface. This is the back surface of the cylinder. That means this surface, right? And there we can see initiation of the vortices or creation of the counter rotating symmetric vortices. Now coming back to our discussion, if we keep increasing Reynolds number, we can see these vortices, symmetric vortices, to grow. And exactly this is the scenario at Reynolds number around 40. And I have written here also, symmetric vortices are found till Reynolds number around 40 because, again, depending on accuracy of measurement, accuracy of performing the experiment, getting absolutely, streamline flow upstream of the cylinder. Then what happens to downstream? Measuring exactly everything correctly, mapping it, and then plotting, we observe little variation between the results from place to place, from experiment to experiments, from numerics to numerics. Prandtl did this historical experiment. He found 45, this value. This experiment was repeated by Roscoe in Caltech. He found 47. Subsequently, many people have repeated this experiment. Some people have got 47, some have got 48, even some have gotten 50. Same about the numerics. This, depending on the numerical error, finally, the computations also converged in that range. Some people got symmetric eddies up to Reynolds number of 47, some people got up to 49, but let us say almost all the correct computations concluded that around Reynolds number of 50, the symmetric vortices are found, but around that means either 47 or 49 or 50, asymmetry creeps in, and this asymmetry basically cause a bifurcation in the flow, and this bifurcation is called half bifurcation. And then the vortices tend to shed. They are no longer steady sitting vortices. They tend to shed into the stream. And there are many other happenings. Let us go through that. Now, interesting sequence of events begins to develop when Reynolds number is increased beyond 40, at which point the wake behind the cylinder becomes unstable. Photographs show that the wake develops a slow oscillation in which the velocity is periodic in the downstream distance. So, velocity, for example, v velocity, if you go along the symmetric plane, it is supposed to be 0 because of symmetry. But since the symmetry is broken, vortices are shed, and this velocity become periodic. You will see periodic variation of this v component of velocity, from which we can get also some time period, and some frequency. With the now velocity is periodic in time and downstream distance, with the amplitude of oscillation increasing downstream. The oscillating wake rolls up into two staggered rows of vortices with the opposite sense of rotation. Quite clear, because here also vortices, basically earlier also, they have opposite sense of rotation. They were trying to peel off and they are brought back to this, this point by the external flowing stream. So here sense of rotation is, one can say that basically this is clockwise rotation. But similarly, this vortex then will have counterclockwise rotation. So sense of rotation are different. So when they are shed into the stream, this will keep on continuing. So basically wakes roll up and two staggered rows of vortices with opposite sense of rotation they are found. Karman, Theodor von Karman, as I mentioned it earlier, he was a student of Professor Prandtl. After the Second World War, he came to United States and he was in jet propulsion lab. He became one of the world leaders in fluid mechanics. Karman investigated the phenomena as a problem of superposition of irrotational vortices. He concluded that a non-staggered row of vortices is unstable and a staggered row is stable only if the ratio of lateral distance between the vortices to their longitudinal distance is 0.28. Because of the similarity of the wake with footprints, because of the similarity of the wake with footprints in a street, the staggered row of vortices behind a bluff body or blunt body is called von Karman vortex street. The vortices move downstream at a speed smaller than the upstream velocity u infinity. This means that the vortex pattern slowly follows the cylinder if it is pulled through a stationary fluid. And this is the likely picture of a vortex street behind a cylinder, and this is of course artist impression from the photographs and from the numerical studies, some conclusion, and such vortex streets are observed between Reynolds number of 80 and 200. In the range of Reynolds number 40 and 80, the vortex street doesn't interact with the pair of attached vortices. As Reynolds number is increased beyond 80, the vortex street advances closer to the cylinder and the attached eddies whose downstream length has now grown to be about twice the diameter of the cylinder themselves begin to oscillate. Finally, the attached eddies periodically break off alternately from the two sides of the cylinder. While an eddy on one side is shed into the stream, that grows on the other side, resulting in an unsteady flow near the cylinder, in the near wake of the cylinder. As vortices of opposite circulations are shed off alternately from the two sides, the circulation around cylinder changes sign, resulting in an oscillating lift or lateral force. Usually, if we imagine flow around a cylinder and the flow is perfectly symmetrical, we are not supposed to get any lift. But here we can clearly see that circulation around the cylinder changes the sign, and then it develops positive lift and negative lift periodically. If the frequency of vortex shedding is close to the natural frequency of some mode of vibration of the cylinder body, then an appreciable lateral vibration has been observed to result. Engineering structures such as suspension bridges and oil drilling platforms are designed so as to break up a coherent shading of vortices from the cylindrical structure. As such, same is observed in bridge piers also. This is done so in order to break these coherent vertical structures. What is done, basically some spiraling path is inserted, spiraling blades protruding out of the cylindrical surface that is artificially made, to break the span-wise coherence of shading. The passage of regular vortices causes velocity in the wake to have a dominant periodicity. The frequency n is expressed as a non-dimensional parameter known as Struhal number. So Struhal number, named after Struhal, again, who first observed it. As such, he observed the hanging wires due to this vibration, vibrating noise, musical sound. He first listened to that and gave its scientific interpretation. And so this Struhal number is the frequency into d by u, just to non-dimensionalize it with respect to velocity and the diameter of the cylinder. It is called Struhal number. Experiments show that circular cylinder with the value of S remains close to 0.21 for a large range of Reynolds numbers. For small values of circular small values of cylinder diameter and moderate values of V, the resulting frequencies of the vortex shading and oscillating lift lie in the acoustic range. For example, U equal to 10 meter per second and a wire diameter of 2 millimeter, the frequency corresponding to a Struhal number of 0.21 is n equal to 1050 cycles per second. The singing of telephone and transmission lines has been attributed to this phenomena. I mentioned about it, the singing of transmission lines that was identified by Struhal, and that is why this shading frequency is named after him. It's sometimes and often is called Struhal frequency. Now let us come back to heat transfer. In order to understand heat transfer on a moderate Reynolds number, not a very high Reynolds number of 3480, we take a recourse to the investigation of Sharma and Sukhatme. This experiment was done in IIT Bombay. Starting with a high value at the stagnation point, nu theta is, Nusselt number at any theta decreases, and it has a highest value at the stagnation point. That means when theta equal to 0. This is one side of the cylinder, this is another side of the cylinder, and finally, we are going up to 180 degree. That means the rearward stagnation point. But, once through the lower side and on another cycle through the upper side. So this is clearly written. This is upper half from stagnation point to 180 degree through the upper half of the cylinder, and then to the lower half of the cylinder, again from the stagnation point to forward stagnation point to rearward stagnation point. So starting with a high value at the stagnation point, nu theta decreases with increasing theta, as a result of laminar boundary layer development. So obviously at the stagnation point, boundary layer thickness is minimum, and then boundary layer is increasing in the flow direction, resistance is increasing, and obviously Reynolds number value is decreasing. Minimum is reached at the point of separation. The point of separation is symmetrical about the forward stagnation point. So for stagnation point, if we go to the upper half and to the lower half, for mean flow, that means instantaneously vortex shading will taking place and flow is unsteady. But if we derive a statistics of mean flow, then we'll found the stagnation point is at 110 degree from the leading edge. If we go after the separation point, nu theta increases with theta. You can see up to 110 degree on both the sides. Nu theta increases with theta because of the mixing associated with the vortex formation in the wake. It may be mentioned that the value of nu theta are the time average quantities. As I said, these are time average quantities. Otherwise, this symmetric structure, when vortex shading is taking place, instantaneous field cannot be symmetric. Now, it may be mentioned that the values of nu theta are the time average quantities. Sharma and Sukhatme, Professor Sukhatme's experiment is this, together with his Diden student, Professor Sharma, also found the correlation between the Nusselt number at the forward stagnation point and Reynolds number as nu, this is forward stagnation point, nu FSP equal to 0.91 into Reynolds number to the power 0.5. Now we will see some experimental results for high Reynolds numbers. High means much higher than this 3480. These are all above 10,000 Reynolds numbers or even more. So Nusselt number is high at the forward stagnation point as usual. The nu theta reduces with the growth of boundary layer and reaches a minimum at 80 degree. So for high Reynolds number flow, the basically separation point moves forward, and from the leading edge around 81 or 82 or 80, depending on again accuracy of measurement, the flow separation takes place. So nu theta again reduces with the growth of boundary layer and reaches a minimum at theta equal to 80. At this point, separation occurs, as you can see, for subsequent, Reynolds numbers here, all we can see that the basically Nusselt number decreases up to the stagnation point around 80, and then it again increases because of mixing due to eddies in the wake. Now, for Reynolds number greater than 10 power 5, the variation of nu theta with theta is characterized by two minima. The decline in nu theta from the value at the stagnation point, first minima, coming up to first minima, is again due to laminar boundary layer development. But the sharp increase that occurs between 80 and roughly 100 degree, this increase in Nusselt number, sharp increase that occurs between 80 and 100 degree is owing to the boundary layer transition to turbulence. With the further development, So turbulence means, better mixing and better transport rate, and we get enhancement of Nusselt number. With further development, and then this is just the transition from laminar to laminar boundary layer to turbulent boundary layer. But then turbulent boundary layer starts growing, has its own growth. So basically, with the further development of the turbulent boundary layer, nu theta again begins to decline. Eventually, the turbulent boundary layer separates around theta equal to 140 degree. So it is very close to the rearward stagnation point. So at 140 degree, and then nu theta increases as a result of, this turbulent boundary layer separates at theta equal to 140 degree, and then obviously, so up to this turbulent boundary layer separation, the Reynolds number will, Nusselt number will decrease, and then again Nusselt number will increase because of separation of turbulent boundary layer. So, and then nu theta increases as a result of considerable mixing associated with the wake region. So overall average condition is, so this is of course the average Nusselt number in such cases, not nu theta. Nu theta is a local Nusselt number. This is basically integration of entire nu theta and then averaging it out, and we can say nu d over bar, average Nusselt number, is h bar, that means average heat transfer coefficient, into d by k, and this is given by c into Reynolds number based on diameter to the power m, Prandtl number to the power 1/3. So, and this is a very famous scientist, Russian scientist Zhukovskas. He did large number of experiments for wide range of Reynolds number, wide range of fluids, and he gave this correlation: average Nusselt number based on duct diameter equal to C, Reynolds number based on duct diameter, cylinder diameter. Here it is cylinder. Sorry for calling it wrongly. It is as duct diameter. It is cylinder diameter. Average Nusselt number based on cylinder diameter equal to C, average Reynolds number based on cylinder diameter to the power m, Prandtl number to the power n, Prandtl infinity divided by Prandtl W to the power 1/4. Now, basically, I will explain all the meaning of all the symbols and notations. C and M are given by this table. You can see that for different Reynolds number range, we have different C and different M. So like, Reynolds number in the range between 4,000 and 40,000, C is 0.193 and M is 0.618. Reynolds number between 40 and 4,000, C is 0.683 and M is 0.466. So this C and M are function of Reynolds number, and in a tabular form that has been given over the range of Reynolds number, what is the value of C and what are the values of C and what are the values of M. Now, all the properties are evaluated at T infinity, that means fluid temperature. So that is why we have written Prandtl infinity. Prandtl W is not to be confused with anything else, but this is at wall temperature. Prandtl number, the mu Cp by K, the values have been taken at wall temperature. And this, when we calculated this Prandtl number, again mu Cp by K, values have been taken at the free stream temperature. So all the properties are evaluated at T infinity except Prandtl at wall temperature, which is evaluated at TW. For Prandtl number less than equal to 10, n is given by 0.37, Prandtl number to the power n. This n we are talking about for Prandtl number less than equal to 10, this n is 0.37, and for Prandtl number greater than 10, this n value is 0.35. Now we will give or discuss briefly some other correlations for small Prandtl number fluids, that means for liquid metals. The local heat transfer coefficient on a flat plate is given by Nusselt number at a given x, that means distance from the leading edge, 0.565, Peclet number x to the power half. Peclet number is basically Reynolds number into Prandtl number. And why x has come? Since Reynolds number is there, Reynolds number should be calculated based on the running length, that means length from the leading edge. So Reynolds number into Prandtl number gives Peclet number, and Peclet number at a given x to the power half, that is basically the relationship with Nusselt number on a flat plate for the flow of liquid metals. From experiments, the local skin friction coefficient for turbulent flow over a flat plate is given by Cfx 0.0592 Reynolds number at a given x to the power minus 1/5. This is the range of Reynolds number is this. To a reasonable approximation, the velocity boundary layer thickness for turbulent flow over a flat plate is given by delta by x equal to 0.37 divided by Reynolds number at the same x to the power minus 1/5. See the difference between the laminar boundary layer growth. If we recall, we got delta by x equal to 5 by Reynolds number x or x to the power half. Here we are getting delta by x into 0.35 divided by Rex to the power minus 1/5. Now delta varies as x power 4 by 5, whereas in the case of laminar boundary layer, if you recall, it was x power half. The local Nusselt number for turbulent flow over a flat plate. So we have discussed about cylinder, but for a flat plate it is NUX equal to 0.0296 Reynolds number to the power 4 by 5 and Prandtl number to the power 1/3. If you recall, for laminar flow it was 0.332 Reynolds number at a given x to the power half, Prandtl number to the power 1/3. Here it is Reynolds number to the power 4 by 5 and Prandtl number to the power 1 by 3. So Rex to the power 4 by 5 and Prandtl to the power 1/3. Now in mixed boundary layer situation, the average heat transfer coefficient for flow over a flat plate where up to some x it is laminar, and then it is turbulent. So we can summarize that as HL average equal to 1 by L, 0 to XC, it is H, heat transfer coefficient for laminar flow dx, then XC to L, remaining part, H turbulent, heat transfer coefficient for turbulent flow into turbulent flow dx. So HL average, if we perform these integrations, we can finally get basically Nusselt number based on the plate length average value is given by 0.66 after performing this integration, 0.664 Reynolds number to the Reynolds number at x critical to the power half plus 0.037 Reynolds number based on the total plate length to the power 4 by 5 minus Reynolds number at xc critical x to the power 4 by 5, entire expression multiplied by Prandtl number to the power 1/3. So finally we get average Nusselt number is 0.037 Reynolds number based on the plate length to the power 4 by 5 minus A into Prandtl number to the power 1/3. If the typical transition Reynolds number is 5 over a flat plate, REX C, critical transition Reynolds number, equal to 5 into 10 to the power 5, then NUL average is given by 0.037 Reynolds number based on plate length to the power 4 by 5 minus 871 into Prandtl number to the power 1/3. Prandtl number to the power 1/3. So similarly, the skin friction coefficient, average skin friction coefficient, is given by 0.074 divided by Reynolds number based on plate length to the power 1 by 5 minus A divided by Reynolds number based on plate length, where A is 1742. This can be calculated from the basic principles as we have demonstrated it earlier. So if the plate length is much higher than the transitional length, then we can say that average Nusselt number based on plate length over the entire plate is 0.037 Reynolds number based on plate length to the power 4 by 5 into Prandtl number to the power 1/3, and skin friction coefficient, average skin friction coefficient based on plate length is 0.074 Reynolds number based on plate length to the power minus 1 by 5. We know that fluid properties vary with temperature across the boundary layer, and that this variation can certainly influence heat transfer. This influence may be handled by one of the following two ways. In one method, all the temperatures are evaluated at a mean boundary layer temperature, that is TF, or we can call it film temperature, where film temperature is equal to the surface temperature plus free stream temperature by 2. In the alternative method, evaluate all the properties at T infinity and multiply the right hand side of the expression for Nusselt number by an additional parameter. This parameter is commonly of the form Prandtl number infinity by Prandtl number W to the power R, where or mu infinity by mu W to the power R, where infinity is basically properties are evaluated at the free stream temperature, and W is signifies that property of the fluid is evaluated at the wall temperature. W designate properties at surface temperature. We'll stop here today. We have almost concluded the external flows, flow and heat transfer in external flows. Thank you very much. Thank you for interest.